All right, since statistics, the beginning of it at least, is all about gathering data, I need us to actually gather some data from our class. So, and I'm going to be showing you the responses. I think I'm still missing one person, but at this point, don't respond because we're going to use this data. Here's what we know, all right? We have all of this information that we have gathered. Great. Statistics now needs me to summarize this data or organize this data in some way. So what we're going to do is on your paper, we're going to look at this first chart that's blank that has all of the favorite classes listed, and we're going to draw a histogram or a bar chart to describe our class's opinions. So if we look at the data, how many people said that math was their favorite subject? 9. So what we're going to do back on our notes is we're going to make 9 tick marks. 1, 2, 3, 4, 5, 6, 7, 8, 9. Pretending that they're all equal because I'm a human and I can't draw very well. And we're going to make a bar chart around the math section that shows the 9 people who chose math as their favorite subject. Okay, if we look back at the data, how many people picked science? Science is red. 2. So back on our notes, we're going to show 2, frequency of 2 for science. We see how this works? Okay, I'm going to leave the data up there so we can all fill it in without me flashing back and forth. For history, how many people chose history? 3. You don't have to color it in, by the way. I just think it's more fun. English, 3. Fine arts, 5. Athletics, 1. And other, 1. Just out of curiosity, who put other in what class? I won't be mad. 9 people picked math. Makes me feel good. Who picked other? Is it you, Ari? Oh, you're just giggling like it's you. If somebody takes welding, I accept the fact that that's probably cooler than math. Whatever, it's fine. Okay. So here's our histogram or our bar chart that displays the information that we just collected from our class. Let's do this again. This time we're going to do this with height. Now height is going to be a little different. Look at what the x-axis here is labeled as. What do you notice? Oh, inches for sure, but like I go 40 and then goes by 5. So what we're going to do this time is not put it like centered on the word other. We're going to put it, any of the frequency responses between 40 and 45 will go here, right? So let's, well, I highly doubt anybody is 40 inches because that's very small. But let's see. How tall are you? What's the shortest response that we got? 59. So if we look at that one, the 59 would fit in between 55 and 60. Now we're going to do this with a lower limit, which means not counting 60. How many people are between 55 and 60? 2. What that means is on our notes, hello, come on, is we will from the 55 to 60 have 2 as my frequency here. Now, our next little bucket here, between 60 and 65, including 60 but not including 65, how many people's height would be there? 1, 2, 3, 4, 5. Correct, 5. So we will now have 5 people, 1, 2, 3, 4, 5, in this section. See how this works? Okay. What about from 65, bigger than 65 and 70? 1. So let me do 1. I'm not going to flip back and forth anymore. From 70 to 75.
6.
We have 6. This is a much taller class than my first period class. So our histogram, our bar graph, would look something like this. Now, our last graph that we're going to be drawing is the number of siblings graph. And this one goes back to being centered at the number because it's not a range. Like, you're not going to have between 0 and 1 siblings. You're either going to have 0 or you're going to have 1 sibling. So let's look at our data here and see for our class how many people had 0 siblings. 1. So we're going to have to draw that in for ourselves. So we'll go 1. One only child in this class. Wait, am I on the wrong one? This says 1A. Oh my gosh, have we been using the wrong data? That's embarrassing. Well, happy Monday on a Tuesday, everybody. How many people in this class have 1 sibling? 8. So we're going to go up the side again. Let me make sure I close the right one this time. So this will be 2, 3, 4, 5, 6, 7, 8. A lot of people have 8 siblings.
8 siblings?
What? Have 1 sibling. You know what I mean? 8 people have 1 sibling. Words are hard. It's a Monday. I know it's a Tuesday. Okay, I'm going to leave the data here now so we can see how we do it. How many people in this class, this is 2A, yes, have 7. What? Have 2 siblings? 7. I mean, theoretically, these should all be the same width, right? Yeah, we're just human. We're doing our best. Y'all are going to laugh at what mine looks like when I show you my notes again. How many people in this class have 3 siblings? 4. How many people in this class have 4 siblings?
1.
And how many have 5 siblings? Okay, so beyond just organizing data, we're also going to need to be able to summarize or describe the data that we've taken when we do statistics. So I haven't defined almost any of these words for you yet, but what's nice about stats is that the words that we use to define things sound like exactly what they are. So what I'm also going to have us do is decide whether the data that we've taken is qualitative or quantitative. What do you think the word quantitative is telling us? What does it sound like? Quantity. When you do a quantity of something, what are you doing? There's numbers. When you hear the word qualitative, what do you think of? And does that make you think of numbers? What does it make you think of? Okay. Food? Somebody's hungry. How about like descriptive words? Yes? Quantitative data is a numerical data that we've taken. Qualitative just describes something. So in this first instance, when we were asking you your favorite class, is that quantitative or qualitative? Did we do a number or did we just do a word? A word. That makes this qualitative data. Because your favorite subject is a quality about you. What about height? Quantitative. You responded with a number. That's so funny that it's the wrong data. Sorry. What about the number of siblings? Did we use numbers or words? Numbers, which makes this quantitative. And then beyond that, beyond just qualitative and quantitative, we can also describe whether the variable that we're working with is discrete or continuous. Now these may be not so much sounding like what they are, except that we've used them in mathematics before. A discrete graph was a graph that was just dots, disconnected points, and a continuous graph was one that was connected. So in the same concept, discrete data is data that would be individual dots, things that you cannot take halves or parts of, which include your favorite subject. Favorite subject is a discrete data point. You're not like, I'm half on to math and half on to science. No, you picked a favorite. It is a discrete data point. Your height, however, specifically because somebody put on there 67.2 as their height, we were able to use halves, right? Which makes this continuous data. It's something that we measured instead of counted. So continuous is measuring because we can have halves and parts. Discrete is something that we count. In which case, is your number of siblings discrete or continuous? Discrete, we count our number of siblings. Yeah, so this is discrete data. Again, I haven't defined these things for you, but they make a lot of sense. Would this statistics that we just did be considered to be descriptive or inferential? Let's think about those two words. Descriptive, what do you think it's going to be doing? Describing something. What about inferential? Inferencing. What does inferencing mean? Taking an educated guess. Okay, cool. So from this data, did we do any sort of educated guessing? No. So all that we have done here is some descriptive statistics. We have just taken information and displayed it. These statistics are descriptive because, like you guys said, we are not using them to draw any sort of conclusions. We're just displaying the information, describing the information. Again, I haven't defined this word for you, but it makes a lot of sense. The question says, what is the intended population being studied? What is population? Maybe outside of statistics, what does that mean? Humans, people. Doesn't have to be just humans, though. We usually talk about it in human capacity. And in population, population is describing who we are studying in total. So since I questioned everybody in this class for this, the intended population is specifically the 2A dual credit stats class, because that's where we got our information from. If this survey had been given to all math students at Mesquite High School, that would be the population. That's who we're studying. But I only gave the study to y'all, so that's our population. Now, thinking ahead, this is like later chapters 7, 8, 9, things like that. It said, let's say we want to use this information to make predictions about our entire school. So now our population has changed to being the entire school. I'm going to give you numbers because, again, I've just kind of made these up because it takes us to getting to chapters like straight up 8 or 9 to be able to get these numbers. But let's say an inference we can do or a statistic we can give is that we are 95% confident that the true percentage of the students at our school whose favorite class is math is between 7.3% and 40.7%. This statement gives a confidence rating of the reliability of your data, as well as a mean with a range surrounding it, it's called standard deviation, to give us a confidence interval where we think the actual value lies. Maybe also we would say something like, we are 95% confident that the true mean height of the students at our school is between 62.6 and let's say 67.5 inches. We're 95% confident that the average height of the students at our school would be in this range. This is now the kind of statistics that is inferential, because I've taken data that could have just been described, but I have used it to draw conclusions outside of the data that I actually have in the study. So what statistics will do is it will gather data, summarize it, organize it, analyze it, and provide a reason for a conclusion that is drawn, as well as kind of a measure of error just in case we're a little bit off. That is a true statistic given in a study. Now we're going to have on the next page, literally a full page of vocabulary. Because we got to make sure that when we're using specific words in stats, we're using them correctly. So what is statistics? The very basics. Statistics is the science of collecting, organizing, summarizing, and analyzing information to draw conclusions, which kind of gives us the four main units of study: collecting data, organizing it, summarizing it, and deciding how reliable it is, analyzing. I want you to put like a little boop, boop, boop on the next four words. These kind of all go together to describe the types of things that you're taking studies of. Like we said earlier, a population is the entire group being studied. So we could be talking about the population being the entire world, the United States, the state of Texas, Mesquite High School, or just my students. We choose our population that we are describing. A census, have you ever heard that word before? Census? Do y'all know what it is? When have you heard it used? In the what? Oh, like in the government, yes. The United States government does a census every 10 years where they gather data about every single member of the population. Let me make that word legible. And they are like, you know how we give out like surveys and like we say everybody should do this, but then the three people next to you in class didn't fill out that survey. A census will be taken when they make sure every single person fills out that survey. You don't send back your census, they call you on the phone and ask you the questions of the census. They have to get this information from every single person to have accurate information in a census. But, yes?
Do they get the homeless people too?
I don't know the answer to that. They don't have a home address, and it's usually sent to your home. Wow, I'm going to go down a deep dive on that on Google later, so maybe I'll answer that question for you. But imagine doing that. So let's say, in a smaller sense, we're trying to get a study done about the students of Mesquite High School, like those little panorama surveys we make you do. Not everybody's going to fill that out, am I right? So it's kind of crazy to think that we can get an actual census unless we have the money and power to do so. So instead, a lot of times, many times, most times, statisticians take a sample, which is just a subset of the population. And this is the group you actually study from the population. So we're just going to take, maybe we're saying we're going to survey all the people at Mesquite High School, but we're actually just going to survey all the people in English classes. That's a good subset of the population. There are still people not in English classes, but it's a good subset of the population itself. An individual is a person or an object that is a member of the population. It's important to note that individual isn't necessarily like a human. Sometimes we do studies on rats, we do studies on cars. Those become individuals in the study. when we're providing information after doing a study, we can either provide a parameter or a statistic. A parameter is a numerical summary of a population. And the easy thing to remember here is population and parameter both start with P. And on the other hand, a statistic is a numerical summary of a sample, which is that subset of the population. And nicely, sample and statistic both start with S. Love that for me. So parameter is for the population, statistic is for a sample. The two types of statistics that we'll talk about in class are your descriptive and your inferential. We've already talked about these, but let's formally define them. Descriptive statistics is a description of gathered data from a sample, whereas inferential statistics is when you take the result from a sample, extend it to the population, and measure the reliability of that result. Give a confidence rating. Then we have our data types. Qualitative data or categorical data, sometimes you'll see it called, classifies individuals based on some characteristic, which is normally words. Like, my favorite subject is math. My favorite subject is reading. My favorite subject is science. Those are words that we can classify individuals based on. Quantitative data provides numerical measures of the individuals, which is usually given, or always given, in numbers. Then those qualitative and quantitative data measures can be discrete or continuous. A discrete variable is a variable that has finite or countable number of possible values. So you count tickets. Can't sell somebody half of a ticket. You either have the ticket or you don't. That's a countable individual. Continuous variables, however, are a variable that has an infinite number of possible values, like height. We can measure to the 1,000th or the 100,000th of an inch. That gives me an infinite number of options to be measuring on. They can take on any value in a given interval. Continuous are usually things that are measured. Discrete is things that are counted. That's the main difference there. Woo-wee, that's a lot of vocabulary. We're halfway through today. These first few days are very heavy with vocabulary just because we got to get the language of statistics down. Okay, continuing with our data from earlier, what if we wanted to do more than just gather the data and put it in like a histogram, a bar chart? Sometimes we want to know how two or more things may impact each other. We could compare to see if your height has an impact on your favorite subjects. Okay, so I just went through our data. And if we're thinking maybe that the taller people are more likely to prefer athletics, let's see if our data supports this. Here's the survey that said that their favorite subject was athletics. Here's their height. Is that on the tall side of all of our height? Let's go responses. I need to look at the summary. Our tallest person was 73 inches. What was their favorite subject? Let's see if I can find it. That's 72. These are very accurate, friend. Well, I'm assuming it's Arthur. Arthur, what was your favorite subject?
I put, well, for fine arts, what culinary do you?
I would have put that in other.
Other. So
That was other. Okay, so the tallest person in our class picked culinary, and somebody who's an inch shorter is the one who picked athletics. So can we draw a conclusion that height would have an effect on our favorite subject?
Maybe.
Maybe, but like not really, right? So does height impact our favorite subject? It's not necessarily true for our data, because if that was true, we would think, one, the tallest person would have picked athletics, and maybe the top 4 tallest people would have picked athletics. In the example they had in the book, the tallest person did pick athletics, but then somebody who was 5'3" picked athletics. They probably play volleyball. So height doesn't necessarily have an impact on your favorite subject. So it does not appear It does not appear to be so, considering that the tallest person picked culinary and the next tallest person picked athletics, right? Would this question be a part of an observational study or an experiment? Yeah, we haven't defined these yet, but like, did we change anything about this, or did we just ask questions? We just asked questions. That makes this an observational study. Hello. Observational study. An observational study because we did not do any sort of treatment or try to influence the individuals. We just asked them questions and looked at the responses. Again, we haven't defined these, but the way that they're written makes it pretty easy to figure out what they mean. What would be the explanatory or response variable? What do we think an explanatory variable means? Explanatory. It explains what change is happening. So it's like our dependent variable. It's what we are changing, independent variable. It's like what we are changing to see if the response variable changes. So the explanatory variable is height here, because we were trying to see if by changing the height, we could affect somebody's favorite subject. Basically, our input was height, our output was favorite subject, and we thought there was an effect here, an explanatory variable. Now this next question is interesting. It says, could we prove that height is causing a change in preference? I would put a little box, underline, maybe a highlight on the word causing. That's a huge word in statistics. Specifically because we chose this to be an observational study, we have to say no. Well, one, our data didn't support it anyways, but even if it did, no, it would just be a coincidence. Main idea here, we would have to do an experiment to prove cause and effect. Since we just had this observation, from observational studies, you cannot determine cause and effect. You can find association, you can find coincidence, but you cannot claim cause and effect when all we've done is observe. But what would it look like to make one of these actual experiments? Let's say we wanted to find out if how much sleep you get impacts your GPA. And we want to design an experiment to do this. What would be the explanatory and the response variables for this question? Which one is which, though? Very good. So the explanatory variable is amount of sleep, because we want to see if that has any effect on your GPA. Now, when we're creating experiments, we have to start to control variables. What variable could we control, and how would we control it to turn it into an experiment? Well, we want to control the amount of sleep somebody gets. So if we were controlling amount of sleep, how could we do that? How do we control how much sleep somebody is getting for an experiment? Force them to have a bedtime. What else? And wake up time. So now we can control multiple groups. One group sleeps for 8 hours, one group sleeps for 4 hours, one group sleeps for, oh my gosh, please not less than 4 hours, but it's an experiment, we'll try it. Y'all should sleep more than that, okay? Now, cool, we have this whole thing set up, but what other variables haven't we mentioned that might have an impact on this study? Because all we're doing is controlling how much sleep somebody gets. Then we're going to look at their GPA.
Like the teachers in the class.
Teachers and classes they take. What if they take like all regular versus all AP classes? So teachers versus, or teachers slash classes. What else could have we not thought about controlling here that would change maybe our results? Extracurriculars. What else?
Learning disabilities.
Okay, learning disabilities. Give me a few more.
Relationships.
Okay, relationships.
I'm gonna be sick on the cover while you're on my book. I'm just saying.
Anything else y'all think of?
Time management.
Oh yeah, extracurricular.
If they have a job, general time management,
Oh yeah, I didn't know what to say.
and then in general, just like family situation, right? All of these things that could actually have effect on GPA that we are not controlling for in this study. So a well-designed study would put controls in for these different things to try to mitigate the effect that differences in these variables might have on GPA. So let's say we ran this study and we found a connection between sleep and GPA. We found that the more you sleep, the higher your GPA, which is, theoretically, I didn't run this experiment, but seems legit to me. Am I right, everybody? We should be sleeping more. I contacted every single one of you. Sleep more. Could we say that more sleep causes a better GPA?
No. Less sleep, honestly, because you get to study more.
Here's okay. Let's say we found out that more sleep does have a significant change on the GPAs of people in the study. Could we say specifically that more sleep causes better GPAs? This one's a yes. What's different about this study from the last study when we had to say no to causing? It's an experiment. Because we did an experiment and not an observational study, we are able to have causation. However, the list of things that we did not control is pretty large. We would, if this was a study we were really doing, we would have to control for those other variables. And the ways we could do that. Y'all know how when you fill out a lot of surveys, a lot of times it asks you for your age range, like all of these like demographical information. It's because the statisticians who are looking at it are looking to compare apples to apples. So they're not going to compare an 18-year-old's answer to a 60-year-old's answer. Y'all are in different groups. That's not controlling for age. So you'll see that in studies if you say, bless you, controlled for age, this is then the conclusion. That means you're looking at more comparable data because we've controlled the variables in the study. Time for some more vocab. Again, I'm so sorry. This is a really dry day because it's just got a lot of vocabulary, but we have a lot of things to get on the same playing field with when it comes to stats. The explanatory variable and the response variable, you guys have got this, but let's just formally define them for a second. The explanatory variable is the variable that you should and can control. This is what you change in an experiment to see if the response variable changes because of the changes in the explanatory one. When graphing, this is typically your x value, your independent variable. The response variable, however, is the variable that changes based on the explanatory variable. This is what you are measuring, and it's typically your y value, your output, your dependent value. Again, we've kind of talked through these, but a formal definition of observational study and designed experiment. An observational study measures a response variable without trying to influence either the explanatory or response variables. Just kind of looking at the information with no intervention. On the other hand, a designed experiment is when you actually go in there and intentionally manipulate the explanatory variable to see if it will impact the response variable. It's very important, and we're going to talk about this next class, is that this must include a random assignment of treatments. Now, we discussed this a little bit already too. We didn't define it, but remember when we made that list of things that might actually affect sleep and GPA? Those are called confounding variables. It's a variable that was considered in the study but whose effect cannot be distinguished from the intended response variable. So like maybe perhaps without controlling for students who have a job, those with a job are going to have a lower GPA if we're forcing them to have a certain amount of sleep. Things like that. That's a confounding variable. On the other hand, a lurking variable is an explanatory variable that was not considered in a study but could actually affect that response variable. So let's say we did the entire experiment. We're done. We're showing our conclusions, and somebody's like, okay, but what about natural IQ? We didn't even consider to control natural IQ when starting the study. That could be a lurking variable in our study that we didn't consider when we started. Association and causation, again, words we've discussed but didn't really go formally define today. An association is when there is a connection proven between the explanatory and response variable. Just a connection of some sort. But causation, because the word cause and effect in there, is when a designed experiment produces results that show an association, we can claim a cause and effect relationship. This is not possible to do with simply an observational study. Observational can only show a connection, an association. Experiments are the ones that can show cause and effect. These last three we haven't discussed at all, but when we're talking about designing experiments, there's three main types of studies you can perform, and they each have characteristics, obviously, but benefits to them. A cross-sectional study is a collection of information from individuals at a specific time or over a very short period of time. Cross-sectional study. So very specific time or very short period of time. A case control study is a retrospective. Do we know what the word retrospective means? Do we know what the prefix retro means? Old. Okay. It's looking back. So retrospective means I want you to think back on your family history or your medical history and answer these questions about the last 10 years of your life. That would be a retrospective study. On the other hand, a cohort study is a prospective. It's the opposite of retrospective. It's looking forwards. So a prospective study in which groups of individuals are chosen and data is gathered over a long period of time. So there are three study types. Cross-sectional is like now. Case study is retrospective, so the past. Cohort study is long-term in the future. So the kind of questions you're going to get, at least in this first section, is just to read about a study and describe it and apply these definitions towards it. We're going to start off with a very short study and then start to add more and more information for you. Because the more information you have about the study, the better conclusions you can draw. So number one says, suppose the average salary of all employees in the city of Joliet is $78,302. City officials took a sample of 30 employees in the city and found that the average salary among those employees was $75,338. What is the population of interest?
Workers of Joliet.
Yes, so all employees of the city of Joliet, assuming I'm pronouncing that city name correct. What are the individuals in the study? That's just a single employee. Seems silly to ask that question, but again, if you're studying cars, individual is now an object, so it's good to define what specifically is being studied for each data point. What is the variable of interest? So what are we studying about these people? Average salary. What is the sample that we took? 30 employees. Typically, they'd give you more information about how those employees were chosen, but simple. We're starting off simple. We were given two numbers besides the 30. Two numbers, $2 amounts. One of them is a parameter and one of them is a statistic. What number is a parameter? Does parameter describe the population or the sample? Population. So which number up there describes the population? 78,302 is the average salary of all employees. That's my population. And we have a statistic that describes a sample. What is the average salary of my sample? Correct. Would this data be considered quantitative or qualitative? Quantitative, it was a number. Is it discrete or continuous? Continuous money is usually continuous because you can make like 50 cents. You can make 33 cents. So it would be continuous data. Is the provided statistic descriptive or inferential? We implied something? We drew a educated guess? Or did we just describe the population? That is a descriptive statistic. Number 2. Notice that we're now getting more information in the little blurb. It says researchers wanted to determine whether there is an association between mobile phone use and brain tumors. To do so, 791,710 middle-aged women in the UK were followed for over a period of 7 years. During this time, there were 1,261 incidences of brain tumors. The researchers compared the women who never used a mobile phone to those who used mobile phones and found no significant difference in the incidence rate of brain tumors between the two groups. Was this an observational or experimental study? Observational. Very good. Why is it observational?
They had data and then they
For experimental, we have to designate treatments. Did we tell some ladies, you use your phone for 8 hours a day, you use your phone for 4 hours a day, you don't use your phone at all? No. That would have been an experiment, but we're just looking at the data. That's an observational study. So it's observational because there was no treatment or influence involved. What are the explanatory and response variables? What are we thinking causes something else to happen? Phone usage might have an association with tumor rate. So explanatory variable is phone usage, and response variable would be brain tumor. That's not how you spell tumor. Let me try that again. What are some possible confounding or lurking variables in this study?
medical history.
Okay, yeah, like family history, medical history of cancer. What else did we not control for? Type of phone, okay, yeah. I heard somebody else say something, but I missed it. Age. How about like diet and exercise? All those sorts of things. General overall health, we didn't control for any of that based on the information we were given. What's up? Pollution where they live. That's a good one. So environmental factors. If they had found a difference between the groups, they found no significant difference. But let's say they had found a difference between the groups. Could they say that mobile phones cause brain tumors? Let's go back to the question, what kind of study did we do? Can we do cause and effect from observational? No. So even if we found a significant influence there, we could not say causation because this was observational. What type of study is this? Cross-sectional, case control, or cohort? Remember, it kind of has to do with timing. How long did this study last? 7 years. Multiple years is a long time for a study. So this is actually a cohort study. Because it's done over a long period of time. right, last example here. It says researchers wanted to determine whether there is bias in clinical practice among patients with cardiac chest pain. In the study, several doctors were independently asked to recommend treatment for a white male patient and for a black female patient. The patients were of similar age, wearing similar attire, and expressing similar physical complaints. The results of the study showed that the black female patient received recommendations that would have resulted in undertreatment, while the white male received appropriate treatment recommendations. Is this an observational or experimental study? Did we influence it in any way, or did we just look at the data? This one is an experiment. We set 2 levels of treatment here. First treatment being a white male versus a black female. Those were the 2 levels of treatment that we are looking for differences in between to see if that caused a change in the response variable. Speaking of those variables, what is the explanatory and what is the response variable? So what did we change, what did we affect? That would be the explanatory variable, and what we measured would be the response.
The recommendations.
We changed, in the 2 groups, we changed gender and race. And what were we measuring at the end of this experiment? The recommendation for clinical practice, yeah. So treatment recommendations. Now, we did try to control some of the confounding variables. What are some of the things they said were controlled amongst the 2 groups that we created? What were the same about them? So we made sure they were the same aged patients, had them dressed similarly, and made sure that they were saying the same physical complaint when they got there, because describing your physical complaint differently can result in different treatment. So physical complaint. Which confounding variables were not considered and could be lurking in this experiment? What are some things that might change what treatment you're given that we did not control for? Allergies. What else? I'm thinking like weight. We didn't control for weight. Genetics, family history. I didn't have this written down, but my last class, this was a good one. They said doctor's training. So if a doctor had been trained differently, we didn't control for the doctor giving different recommendation. So in any survey you do, in any experiment you do, there will be confounding and lurking variables. The job of a statistician is to try to control for as many as possible to really weed out other things that could have caused the undercoverage, undertreatment, as opposed to what we're actually studying. In part D, can the researchers say that gender and race cause different treatment recommendations? Again, cause. Can we show from this experiment, can we claim causation? Why, yes. Yes, because it's an experiment. This is the first time we've had an experiment. However, because we didn't control for all confounding and lurking variables, and we changed 2 things about our studies. We changed both the race and the gender of the patient. We don't know whether it was the combination, one or the other. So this study would probably have to be revisited to really weed out what actually caused the undertreatment, and maybe trying to consider these other lurking variables that we didn't consider the first time. So yes, because this is an experiment. However, we would need to control the variables better. So almost any statistical information you're given, it is good to read the statistics to see how they controlled the experiment that they're claiming this causation from, to make sure it was a well-run study. Otherwise, numbers can do what we want them to do, and it could be crazy. We want good data. We want good math.